how many of you have never heard of enthalpy? Every one of you has encountered enthalpy in your high school chemistry course. Okay? The goal of my lecture for the next 15 minutes is to explain to you what is enthalpy, why do we need another state function. We already have internal energy as a state function. Why do we need another state function? So we just proved that W is equal to minus P delta V. So if I were to write the first law of thermodynamics for a closed system, what would it be? Delta E equals Q plus W. All right? But I can make this very specific and say, so this is WPV. This is the pressure volume work. So W can consist of PV work plus W non-PV work. So please follow along here. My outline here is not very good. I just realized that, so I'm going to change the outline later. So please follow along in this on the blackboard here. Okay, everybody understanding me? Yes, Anna.
So it's WPV plus WPV. What does it say?
Non-PV. Non-PV.
What is that?
So this is pressure volume work. This is non-pressure volume work.
And why do you have to do it?
Because work can be of two kinds. Pressure volume work and everything else that is not pressure volume work, we're going to lump together as non-pressure volume work. For example, electrical work would be in here.
How would you find that?
It's not something that we're going to find, okay? At least not in this course. So, if we have a constant volume process, so this is for a closed system. If we have a constant volume process, how will this equation change here? If volume is constant, work is equal to? Work, PV work is 0. So if you have a constant volume process, delta E is equal to Q plus W non-PV. And only if non-PV work is equal to 0, if non-PV work is equal to 0, then what will this equation become? Delta E is equal to Q. Very, very important result. What does that equation mean? Thank you, Frida. You randomized it, Frida?
Yep.
Very good. What does this equation tell us? Yes, Angela. Okay, that is Correct, but you need to add a little bit more. You said if there is no work, then the change in internal energy is equal to the heat absorbed or released in a chemical reaction. Anna?
Okay, I don't know if this is on the right track at all, but I was going to say something about state function. How like it would be like initial and final.
Yeah, you can say that, that's true, that Q is going to act like a state function. Q normally is not a state function. But under these very special conditions, Q acts like a state function because E is a state function. But this equation holds under two conditions. Angela mentioned one condition, and that is that the non-PV work is equal to 0. What is the other condition? Yes, Lauren?
So the volume doesn't change?
The volume doesn't change. So this equation applies to any isochoric process which does not involve any non-PV work.
Wait, isochoric?
Isochoric, which means constant volume. So if you had a bomb calorimeter, which is a good example or the only example that we encounter for an isochoric process, then if you measure the amount of heat absorbed or given out in a chemical reaction, then you have the change in internal energy for that process. We want a similar equation now for an isobaric process. Because most chemical reactions, 99.99% of the chemical reactions are conducted under isobaric conditions. What does isobaric mean? Constant pressure. So what we want, the final answer that we want is delta X is equal to Q, and X is going to be our new state function, and that state function is what we're going to see very shortly is going to be enthalpy. So this is the equation that we want, which is going to be quite similar to this equation. So under what conditions would you have here? Constant pressure and no non-PV work. So this is the answer we are looking for. So then the question is, what must H be? How should we define H such that this relationship holds? Sorry?
Why wouldn't there be work?
If there was work, if there was non-PV work, then this equation will not hold. If there was non-PV work here, then this equation would not hold.
But you said it was an isobaric, like in terms of from yesterday's lecture, there was like that plastic bag. That
right, but look at this. This is non-PV work.
Oh, okay.
That plastic bag, that work is PV work.
Oh, okay.
Okay, this is non-PV work. All right. So what must H be such that we can have this equation? And the answer is H must be equal to E plus PV. And I'll prove that. I will show you how you can go from here down to here. This is the definition of enthalpy. Why do we define enthalpy this way? Because we want the final answer to be this. Questions? This is really the heart and soul of the concept of enthalpy. If you understand this, then everything else is just additions and subtractions. And you've done lots of those questions in high school. You've done lots of questions with enthalpy, but really not understanding what enthalpy is and why do we have this state function. So we can easily visualize what internal energy is. It's the sum of all the energy contributions, the vibrational energy, the rotational energy, the potential energies, all of them added together is E. E is easily visualized, but PV is not easily visualized. So enthalpy cannot be visualized. It's a mathematical construct. It's purely a convenient definition so that we can end up with this equation here. It is purely a mathematical construct, whereas internal energy is something that you can easily relate to. Enthalpy is not. Okay, so if H is equal to E plus PV, what is delta H going to be equal to? Delta E plus
delta V.
Okay, if you've taken calculus, you would realize that this is taking the derivative of a product. Yes, Laura.
But isn't this for constant pressure?
Yeah, I'm coming. I'm starting with the most general case. I'm getting there.
Okay.
Okay, you're one step ahead of me. All right, so here is what Lauren is saying. This is constant pressure. So Lauren, what does this equation become now equal to?
Delta E equals...
Delta H equals?
Delta H equals delta E plus delta VP.
Sorry?
Delta VP.
Delta, sorry, so this is... Oh, no. Sorry. Yeah. Okay. This is,
So
okay.
P times delta V.
P times delta V. Okay. Let's, on this side here, write delta E is equal to Q plus W. Where did that come from? Angela? The first law of thermodynamics, and this is for a closed system. All right? That's going to be equal to Q plus W PV plus W non-PV. But we're working with no non-PV work, so this is going to be equal to Q plus WPV. This goes to 0. So delta E is equal to Q plus WPV. But WPV is minus P delta V. All right? So therefore, this becomes equal to Q minus P delta V.
Here? Why is it happening?
So I'm just substituting for WPV. WPV we proved last time
Oh.
okay, is minus P delta V. So now I have Q is equal to delta E plus P delta V. So I'm going to put an asterisk here. I'm going to put an asterisk here. Compare the two asterisks, and what do you get? Delta H is equal to Q. Very, 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 very important result. For a constant pressure process, if there is no non-PV work, the amount of heat absorbed or given out in a chemical reaction is equal to the change in the enthalpy. And you're going to make this measurement in lab. You're going to do a reaction under constant pressure conditions, and you're going to measure the heat that is released, and that measurement is going to give you then the change in the enthalpy. This is the explanation as to why we need a new state function and what is the definition of that new state function. We define it this way such that we end up with this final result. This is the final result that we want. So it's a matter of convenience how we define enthalpy. Questions? Yes, Erica.
And then, so just to clarify, the reason we can get rid of the delta PV is because delta P is 0.
Right.
There's no change in pressure.
This goes to 0.
Okay.
So what I said is elegantly summarized in this equation here that is underlined. A thermochemical equation is a chemical equation that is balanced and also has next to it the change in the enthalpy. And here is an example of one. Here is another example. Quite often, we have fractional units here, so that a fractional stoichiometric coefficient, so that the stoichiometric coefficient here can be 1. But if you take any equation, any thermochemical equation, and multiply it by some factor, then you have to multiply the corresponding enthalpy change by that same factor. You've done that many, many times in your high school chemistry course. All right, let's go to lecture number 18. All right, so we are very interested in the enthalpy changes for chemical reactions, but we don't want to be making measurements of Q for every reaction under every set of conditions possible. you could fill all of the books in the entire earth with just information about one reaction, information about the enthalpy change at different temperatures and different pressures. We don't want to do that. We want to only specify the enthalpy change of a reaction at a certain temperature and a certain pressure. That's what we want to specify in a set of tables. If we think about all the different temperatures and all the different pressures that are possible, then we would fill entire libraries with this information. So we define a quantity called, or a concept called standard states. And a standard state of a substance is the pure form of that substance at 1 bar. What is 1 bar? Sorry, Lauren? Tamara?
1 atmosphere of pressure.
1 bar is approximately 1 atmosphere. It's not the same. 1 bar is equal to 10 to the power 5 pascals. 1 atmosphere is equal to 101,325 pascals. Okay, there's a slight difference, about a 1% difference. So the standard state of a substance is the pure form at 1 bar of pressure and a temperature usually specified as 25 degrees centigrade. And for a solid, the standard state is a pure solid at 1 bar. For a liquid, it's a pure liquid at 1 bar. For a gas, it's an ideal gas at 1 bar partial pressure. I'm not going to define what the standard state is for a solution. That's something that you will encounter in Chemistry 205. So I explained to you just now, why do we need standard states? If we don't have standard states, we're going to fill all of our books with information for just one reaction. We don't want to do that. So now we're going to define a quantity called standard enthalpy change, and we denote the standard by putting a superscript 0 here. That's our clue that we are talking about standard states. So when we say delta H naught, we mean that the reactants are in their standard states. So methane is at 1 bar, oxygen is at 1 bar, carbon dioxide is at 1 bar, and water liquid is at 1 bar. When the reactants and products are in their standard states, the enthalpy change is called the standard enthalpy change. And these are the values that are tabulated. Not the enthalpy change at 2 bar, not the enthalpy change at 5 bar. There are equations that one can use to convert from 1 bar to 5 bar, but we won't learn those equations. Yes, Anna?
Whenever we're given an equation that has the enthalpy change at the end, that means that it's at standard.
That 0 is very important there.
Oh.
Okay?
So if it doesn't have the 0,
then it's kind of ambiguous. All right? So there are various different types of enthalpy changes. One of them is called enthalpy of combustion. If you take 1 mole of a substance and burn it in oxygen, the amount of heat released is called the enthalpy of combustion. So can you balance this equation here, please? How can you rationalize the discrepancy between the value here and the value here? Yes, Tamara.
Because the value in the table is looking at when you have 1 mole of C2H2, but
Right.
the one in the table is looking at 2 moles of it.
No, the one in the equation is looking at 2 more.
The one in the equation is looking at 2, the one in the table is looking at 10.
Exactly. Did everybody understand that?
Could you
The,
repeat that again?
the value that is given here, acetylene, ethyne, okay, is minus 1,300. That's for 1 mole. That's the definition of enthalpy of combustion. But the equation that I'm writing here has 2 in front of here. And therefore, the value here is twice the value that is in this table.
Can you balance the equation?
Okay. Can somebody help me out here? 2C2H2 plus 5O2 is going to go to CO2 plus H2O. It's going to be 4CO2 to, very good. Okay, so we talked about enthalpy of combustion. Now let's talk about enthalpy of formation. This is a very important enthalpy because most often what is found in tables are the enthalpies of formation. And you can use the enthalpies of formation to calculate the enthalpy change for any reaction that you might be interested in. Okay, so the definition of the enthalpy of formation is the change in enthalpy associated with producing 1 mole of a substance from its elements in their standard states. I should have also said in the most stable form of the elements in their standard state. So can you write down what is the enthalpy of formation of dinitrogen gas? Can you write out the equation and figure that out, please? So can you talk to your neighbor, please, and convince your neighbor that you're right?
I know there's some cases. Or like another one.
So the answer is dead silence. 0. Who said that? Who said that?
I did.
You did. Very good, Lauren. Why is it 0?
I don't remember.
Tamara,
I remember that they would be zero whenever you're looking at, so if it's an element that's made from its own two parts, then it's zero, because they're the same.
Right, the reactant and the products are the same. The reactant is N2 gas. Look at the definition. The formation of 1 mole of a pure substance from its elements in their most stable form with all substances in their standard states. So N2 gas going to N2 gas is the reaction that we want to figure out the enthalpy of formation of N2. Yes, Erica.
Why isn't it N plus N then reacts with N to create?
No, so the most stable form of the element,
Oh, is N.
N2,
So if there's ever like below
okay?
more stable, this formation.
Yes, Rachel.
When you undergo a combustion reaction, since it always burns an oxygen, does water always have
Yes. Assuming that substance has hydrogen in it. If the substance doesn't have hydrogen, then you won't have water is not a product. Okay, let's do this question here. Can you write out the thermochemical equation that represents the enthalpy of formation of formaldehyde? Okay, can you talk to your neighbor for a couple of minutes, please?
Wouldn't you just put on the CO?
Oh, so you're saying like no, I'm saying H2.
It would just be CO. Why not H2? Oh, H2 is 0, so then you can only do CO.
And well, then you have to balance things. Yeah.
Yeah, and then the other H2 because it's here and so it also has to be also CO. So then you just have H. And then I would know the energy that goes into this.
So the answer is